Hi, this is Luke Robbins, and this is going to be my Milestone 3 demo for Game Engine. So first things first, I'm just going to get this thing running, just to give you a quick demo here of what we've got, because I think the code is really the focus on this one. So we've got our two skin models here. The lighting doesn't look super awesome, but these are some lit models, and obviously they're skinned, and they're following these animations. So for right now, I'm going to hit N to move transitions, and you can see how this guy switches to running. I wouldn't use the word seamlessly, but it does transition in the blend sense of the word. You can see there's some bugginess, like whoop, I think this guy's going to do this. If I hit next one more time, but you can see as he slides, he's kind of getting in position for his next animation. So yeah, there he is moving along there. Alright, so I think the focus of this one is really the code, but here we go, memory tracking past. So let me go into this. So in terms of the compute shaders, let me kind of show you what's going on here. So for our animations, we can, as we're doing our our process animation, just for most of the time, we're going to get the time here, same as before, determine which frames on the CPU, and then we're going to pass off that task to the GPU, Proof Process GPU, which is what we're going to use here. And so we're going to get a compute shader for computing the bones in local space, set that active, send over the uniform of TS, bind the two frames that we just found. So how we do that, this SSBO index, is when I actually load up the frames at the beginning, I tie that array index to each frame that I've just loaded, and I have an array of SSBOs in my .h file. So here I've got the frame data. So anyway, I index into that, so I bind these two groups of bones. I bind the result, the bone results, the local bone mix, and the matrices that are made from that mix. And I dispatch that, and I wait for it to be done. On the compute side, I'm using the group of 20 that we discussed, passing in TS. Here's my bone structs. Here are my four bindings: the input 1, input 2, bone result, and actually matrix result. And then using slurp and mix, we've got our results here. And then once that's done, we have this memory barrier, wait for that to finish, and move on to translating these into world space. So I grab my other shader for computing world bones, set that one active. I pass information about the number of bones and also the depth of the hierarchy, which is what we're going to be using for calculating the world. Our data is already loaded up at the beginning. In the constructor, I just loaded up the inverse pose data, so now all I have to do is bind it. So these comments are old. And now this one, I bind the hierarchy table, which again I loaded at the very beginning. The local bone mass is what I just calculated before, so all I have to do is bind that. So this is the result of the previous step, which is now an input to the world. And then finally, I bind the result buffer. Dispatch that and wait for that to be done, and at this point I have all my bones, all my bone matrices in world space. And on this side, here's my inverse bone poses, my hierarchy table, ints, and my local bones, and finally the world out. And this is just exactly what we looked at in class, just kind of going through the hierarchy table and iteratively getting sort of our relative space here. So once that's done, we have everything in this final bone world. And on the so in terms of actually passing that along to use this in our calculations, when we get to our graphics object class over here, this guy, we're going to find the animation that we're using, get our current animation stack. So for the humanoid is the animation anim data essentially, and that owns the anim stack, which is run or punch or something like that. And so what we do there, if we're not blending, is we just bind that bone world matrices to part 0, and this is going to be actually in our compute, not our compute shader, sorry, our vertex shader. So we got rid of all the things that we were using before in terms of, you know, like BFT and stuff. And so now we just have position, normal texture coordinates, and we still got the bone weight and bone indices. And now all we have to do is index in here this way, and use this bone X inverse, which is the ones that we calculated on the GPU through our compute shaders. So there we go. And then this is just lighting stuff, and then that passes the out color to this guy, and then it does typical lighting stuff. But I think my lighting shader is actually fine. I just think some of the data coming out of the the converter might not be great, especially for the Teddy. So with that done, that's how process animation works. So let me see. So done on the GPU with compute shaders, I showed you. World matrix calculations for the animations, I showed you. Converted to world space. Yep, done on the GPU. So as you saw in here, we're not loading anything up. We just load it to the GPU, and then we never have to use it again. So we just like call set data on, you know, like we set the what was this? Oh yeah, this is just setting up space for the final bone, and this is setting up space for the result, and this is just setting up the hierarchy table data, which was just literally hard-coded for these guys. And this is also when I set the inverse bind pose. So I load all those up a single time, and then I don't have to use them on the GPU. And in terms of the other data, the frame data gets loaded in the animation stack constructor, or the create animation rather. So we just load up from the converter, we load up the frame data, and we can put it into these buckets and then immediately shove it off, to the GPU. So here we go, bone data set, and here we are. We just loop through what we just did, what we loaded up for all the frame buckets, and we can just set that to its corresponding SSBO, and that way we don't have to store the frame buckets on the CPU as we're doing our calculations. And then once again in process animation here, we use the SSBO referring to frame data as opposed to actually using frame buckets. Store the keyframes on the GPU, as I just went over. In SSBOs, that's correct. Lighting, technically yes. And of course, blending transitions. I think I showed you that, but just to be sure. Okay, and then start running. Yep, and it's still called space forget. So in terms of actually implementing blending, so usually I was doing my calculations or my work on the individual class for like run or punch, but because this uses multiple animations, I have to do it on this side. So I modified my anim data to have multiple separate times that I keep track of. So I keep track of the current time, which is like my actual current animation time as I increment here, and then just general management of that. And now I also have a time that I keep track of for the next animation in the list. So this will be start out as 0 and then sort of incrementing as time goes by, so that each of the animations is kind of running next to each other, and then we blend them based on their respective times. So this way we don't have to worry about the time going over for one of them and getting garbage data. And then we also increment elapsed time. So I have what's called transition time, which is what I use as to kind of calculate my TS for the blend. So I'll show you that right now. So here's time updating, and then in the actual blend animation, I will call current animation process, and that will, as a result, that will store that data in its local bone mats for that animation. Call it on the next animation stack, and that will do the same. So that will have those like local, or that local like bone result data. And so then I get the compute shader, the very same one that I use to interpolate between frames, set that active. I'll get T of S, which is elapsed time over transition time, and I just like hard-coded a certain transition time that I thought was appropriate. Set that. And then using the results of the local bone arrays that I calculated for each animation, I bind those as inputs as I would with frame A and B, because these are going to be what's interpolated. And now I bind this guy to, and I actually don't think I use this one, but this is just the bones. And then I bind the bone matrix results here. So this is going to be the blended local bone arrays converted to matrix. And same as you can see here in the local bones, that's just going to be this guy. So I make that, and I dispatch that, and now I have this guy, which is blended bone mats, which is my local bone matrices here. Now I set the world shader again. I set that one active. Again, just like I would do with process animation, I set num bones and hierarchy depth. I set the inverse pose data, and it's just the same exact data as with individual, the same hierarchy table. Now I pass in the blended bone mats, which is the local, as the input, and finally the result, which is going to be blended bone world. Dispatch that compute, and I wait for it to be finished. And at this point, blended bone world is ready to go. So now, if we are blending, we're going to use that. We're going to find the animation, and instead of choosing the current animation stack, we're just going to get the anim data's blended bone world, bind that to 0 in our vertex shader, and that's going to be this guy. And so it will, once I hit N for it to start going, that will just set a flag that tells the animation to use the blending stuff. But in terms of updating it and management, what happens is time will keep going. So once you hit N, like for next animation, the clock starts, and this elapsed time, which is set to 0, starts incrementing. And once the elapsed time hits transition time, which is the length of the blend, it will set this curve time to next time. So basically, so the animation can just keep going. Set that to 0, and then set elapsed time to 0, flip the animation to the next one, so it's just going to be doing process animation, and hit this.blend animation, which is just a flag to false. So once that happens, you can just ignore this, and it's just essentially a single animation running. And the same thing goes on here. It uses the final bone world from single animation stack, and it just kind of works. So we've got compute shaders doing blending and mixing between animations. Everything's done on the GPU with these two compute shaders. We've got a transition of animations, world matrix calculations. Yep. So we get it into local space, then convert on the compute shader. Keyframes are on the GPU, as we saw at the beginning of animation stack, and they are technically lit. And memory leaking is good to go, so no memory leaking. And I think that's it. As always, I can't say it was a pleasure, but it was definitely satisfying to get that going. So I guess this is it.